Alrighty, well, let's begin here. So today's job is to complete these textbook examples 12 and 13. These are examples of what I call meeting objects, meeting object questions. And then I'll give you some time to do some work. I started the handed assignments this morning. I'm almost done. I just have to do the backside. I'm expecting that I should be able to get those done during this period and get those back to you. Tomorrow will be a work period. Somewhere between today and tomorrow, I'll probably do kind of a little quizzy thing just to sort of get a feedback, kind of where you're at kind of thing. It'll just be like, won't be for marks, just sort of a little, what can they do? Where are they? Do I need to spend more time kind of thing? So, probably tomorrow. Probably tomorrow. Okay, so let's talk about Fred and Barney here. Now I'm going to get my notes because I want to make sure that I don't mess this up. Although yesterday I had my notes and it still didn't prevent me from messing up. This is one of my favorite questions, I would say. Fred and Barney are at opposite ends of a 1 kilometer long drag strip in their matching race cars. Fred accelerates from rest toward Barney at a constant 2 meters per second squared. Barney travels toward Fred at a constant speed of 10 meters per second. Completely made up, completely sort of, irrelevant to daily life, but an interesting little exercise nonetheless. How much time elapses until they collide? So ultimately we are solving for t. So we sort of have to do some setup here. Okay. First of all, let's agree that to the right is positive displacement and to the left is negative displacement, right? And you probably don't even need to write that down, but just a little reminder. Okay, now the trick is how much time elapses until they collide? What happens, or how do we know when they collide? From a physics numerical variable standpoint. When the what is equal to what? Not when the velocity is zero. I mean, we're talking about just upon impact, right? Jason? You're on the right track. That's not bad. Let's assume Fred is here on the left. Fred's displacement is positive. Barney's displacement is negative. So let's say they met in the middle. This guy would be plus 500. This guy would be minus 500. That would be a displacement of 0, though, wouldn't it? Right? And if this was 600 and this was 400, then it'd be plus 200. So I think that works, right? Not a bad idea. And good. You're on sort of the right path, but not quite. You're gonna realize it's obvious when I tell you. Where are they when they collide? Can we say that this spot here is 0, and then what would be the initial position of this spot over here? How about we say 1,000 meters? Would that be okay? So where are they when they collide? In the same place, the same position, right? It's when their positions are the same, right? When their positions, yeah, see, I told you to say this, right? When their positions are the same, they're going to collide. But the question is, where is that? Where is that and how much time will elapse? Now, your automatic thought is 500, right? Because Fred is constantly accelerating. Barney's only traveling at a constant 10 meters per second. Okay, so their positions are the same or equal when they collide, right? Their positions are the same when they collide. Look at that. I love that. Now, what is Fred's initial position? Position Fred. 0. He's at 0. Position Barney. Plus 1,000. Position Fred is equal to Fred's displacement, right? Position Barney is equal to what? Pardon me? It's not Barney's displacement. If Barney's displacement is in there, this is equal to Fred's displacement because he starts at 0, if Barney had a displacement of, say, minus 200, what would his position be? No. Because he starts here at 1,000 joy, right? If he goes 200 meters to the left, where is he? 800. So Barney's position is, in fact, 1,000 minus his displacement, right? Whoopsie. 1,000 minus displacement Barney. Right? Is everybody with me so far? Okay. So we're going to have to make these two things equal to each other to find out when they collide. Right? Not in agreement, but you get it. But if you don't, then give me the... I'm not seeing a lot either. Okay, what is Fred's displacement? Fred is accelerating at rest at a constant 2 meters per second squared. So Fred's displacement is equal to, D is equal to VIT plus 1/2 AT squared. Initial velocity of Fred is 0. That's nice. 1/2 of his acceleration, which is 2, which is convenient. T squared, and when you reduce this all down, position Fred is equal to T squared, right? It's pretty simple at the end, right? The 0 disappears, half of 2 is 1, so it's 1 T squared or just T squared. Fred's position is, if he travels for 3 seconds, he's at a spot of 9. If he travels for 4 seconds, he's at a spot of 16, and so on. Simple. Barney's is a little more complicated. He's a troublemaker. So it's going to be 1,000 minus. Now he's traveling at a constant speed. How do we find displacement constant speed? V bar T, 1,000 minus. He's traveling at 10 meters per second, so 10 T. Are those T's the same T?
No.
You're just saying that. Are those T's the same? What does T represent? Time. When this whole situation begins, time is equal to 0. As 1 second progresses, Fred moves in from the left, Barney moves in from the right. Are those T's the same? Absolutely they're the same. Can we set them equal to each other? They are equal to each other. They're the same. Remember, position Fred has to equal position Barney. These two things are equal. We set them equal because they're equal because they collide. They are in the same spot. We want to know what's the value for T when Fred's displacement is equal to 1,000 minus Barney's displacement. Okay, so let's just set them equal to each other. So let's write T squared is equal to 1,000 minus 10T. And do you see where this is headed? Where is it headed? You mispronounced it, Joey. It's yay, quadratic formula. No? Well, we could use our handy-dandy Desmos graphing thing. No, I know. Oh, you want me to do that? Through the wonders of technology. Hey, maybe we could factor that. Are there factors of 1,000 that add or subtract up to 10?
No problem.
10 and 100. You think you think it's kind of one of those ones that you want to spend some time at it, but you think it's probably not worth it, right? Because they're
Like a 20 maybe or something like that.
yeah, but that's not 10. So you got to have closer ones. Yeah, it's kind of weird. I'm just going to go ahead and jump right to the quadratic formula. Minus b plus or minus square root b squared minus 4ac all over 2a. And while you guys are writing that, I'm going to do this. Yeah. What's up?
How can you supposed to get your
minus b is going to be minus 10, plus or minus, square root. B squared is going to be 10 squared minus 4 times a is 1 times c is minus 1,000. I missed a 0. All over 2a. And a is just 1, so 2. Minus 10, plus or minus, square root of, I get 4,100 in there. Did you? Good. All over 2. Now here, use a little bit of logic. I mean, there's two answers. There's plus and there's negative, right? But this is a time, I need time to be positive. So for the whole thing to be positive, if the bottom is positive, then the value on the top has to be positive, right? And so if I go minus 10, subtract square root of 4,100, that's going to be some negative value on top, right? So I'm going to do the add one. I should be able to tell right off the hop that it's the add, so it's 10 plus or minus square root of 4,100, which I don't have. I'll just leave it like this because I don't have that number. And I get an answer of 27 seconds. And if you do the subtraction one, you should get minus 37. Did you know that 27 times 37 is 1,000? I only know because of this question. It's not exactly. Yeah, it's not exactly. Right? It's 27 point something, right? And in fact, you can see that from the graph here. Right? It's 27.02, 37.02. Right? Get you a little closer. Okay. So what does this ultimately mean? It means that Fred and Barney have 27 seconds of playing chicken before they collide. Can you come up with a reasoning? Like what? Does it mean anything here? Fred's way out on one side, Barney's way out on the other. Does it have any meaning at all? One's going at a constant rate. One's going at... No, I don't think... I can't come up with a... I can't even come up with a what would happen in a back-in-time kind of scenario.
It doesn't negative time mean that there's that time.
Yeah, but they would have to share some sort of common position, right? One guy's accelerating at 2. Oh, I guess what would happen is if he was going negative, eventually he'd be going the other direction or something. If that acceleration...
All the way around.
No, it's not that.
Or he was going to the right, and he just caught up with him.
Yeah, it would have to be something like that. Something weird anyway. So. Let's have a look at number 3, or 13, sorry. My nephew, for whatever reason, figures that he should subscribe to my YouTube channel, and he was a little kid, right? And he's watching videos one day, and he sees this video on does Jack catch the bus? And he's like, why are you explaining this? That's okay, and I'm like, well, it's a physics question. He's like, so he starts giving me grief about whether or not Jack catches the bus and who cares or not. I'm like, 8 years old, like, hey, relax, man. Okay, so number 13, Jack is running at 6 meters per second to catch a bus. He sees it start to move when he's 20 meters away. So this distance here is 20 meters. If the bus accelerates at 1 meter per second squared, will Jack overtake it? Yeah, that's a bus. If so, how long will it take him? What's the same and what's different about this question from Fred and Barney? They're moving in the same direction. That's a difference. What's the same? That's true. One is accelerating, one's... Pardon me? They want to be in the same position, right? This time it's not a bad thing like a collision. Jack wants to catch the bus, right? He wants to be in the same position as the bus. So can you set it up the same way? The only real difference in your setup is here's Jack at 0, here's the bus at plus 20. But remember that instead of 1,000 minus the displacement, it's 20 plus the displacement. Do you feel like you'd like to give this a go and give it a try? No? Not by yourselves? Not ready for that? Okay. So position Jack initially is 0. Position bus is at 20, right? And then position bus after is going to be 20 plus the displacement of the bus. This time the bus is the one that's accelerating. So an accelerating vehicle would be VIT plus 1/2 AT squared. Are we good there? Yeah. And position Jack after is equal to 0 plus his displacement. Jack is running at a constant 6, right? So his is going to be 0 plus 6t, right? Velocity times time. And those two things have to be equal, right? When the positions are the same, Jack has caught the bus. So I'm going to have 6t equals 20 plus, oh, I guess I didn't complete this over here. The initial velocity of the bus we're going to have to assume is 0. 1/2, the acceleration of the bus is 1, t squared, so 6t is equal to 20 plus 0.5 t squared. It's really the setup that's important here, right? Like the arithmetic, the algebraic manipulation, I think you can do. It's the how do I put it all together that's the problem. Is anyone feeling real lost? Yeah, real lost? Next step, what do you think? Move the t over, set one side equal to 0. I'm going to put the equal sign right there so Peyton's happy. Should I put the t squared out front? Most people do. 0.5 t squared minus 6t plus 20. I'm not going to go to Desmos right away because I want to show you something first. Put it out of formula though, right? Okay. You want to try factoring something? You can take a half out, you're right. Well, basically what you do is you divide everything by 0.5, right? What do you get over here? 0. So now I'm going to have t squared minus, no, divide by a half. Watch out. Factors of 40 that add or subtract to 12. 4 and 10 is 14. 2 and 20. It's going to have to be some decimal thing, isn't it? Sorry. Minus b is going to be 12, plus or minus. Okay, now actually here's a question. Should I use these numbers or should I use these numbers? Does it matter? It doesn't matter, does it? Are these ones smaller? Oh, it's got a half in there. I don't know. Does it matter? I'm going to use the black ones because that's what I've got written down here. So only for that reason. But you could use either. You could use either. So minus b is going to be 6 plus or minus 6 squared. I heard someone say something. Yes, technically it would. Doesn't matter. So 6 plus or minus, that's going to be, let's just do another step here. 36 minus 4 times a half is minus 2 times 20 is?
Oh, wait, you never catch the buses.
Oh, what did I do wrong here? Something's not working out. Oh no, that's right. Sorry.
Another no solutions. You don't have a.
2 times 0.5 is 1. Uh-oh, what's going on here, Jake?
If you subtract 40 from 36, you get a negative answer. You can't have
Yep. Well, you can, but only in the imaginary world.
Yeah.
Alternate universe kind of thing.
So in parallel universe.
Yes. Yes, on Earth too. No solution. Let's try to spell that right. No solution. In other words, Jack's position is never equal to the bus. Therefore, he misses the bus. Is that right? Oh. What he's go what? I'll look that up. What would that look like in the Desmos world? T squared minus 12t. Would these graph exactly the same? Yeah, they would. Well, let's do this one. 0.5 t squared minus 6t plus 20. You might have to help me remember that. 0.5, 0.5x squared. What is it?
Minus 6.
Minus 6x plus 20. Oh. Yeah, that's weird. There's the graph. No, it means those positions never equal each other, right? Jack would either have to be running faster, or the bus would have to be accelerating at a smaller speed, or they'd have to be a less distance in between. I show that one because I want you to see what happens when you get that negative root. That means that those positions are never the same. They never catch, never collide. Okay? Okay, so here's some textbook ones that I'm sure you will enjoy. Page 64, numbers 1 to 3. And then there's a whole ream, and don't freak out on me. I'm just suggesting these are the textbook questions that are suitable for you to study with. I'm not suggesting that you do them all. That's a lot. I get that. I'm just saying there's a section in the book that matches what I've been talking about. Now, these ones you should avoid. 50, 54, 55, 60, 67, 69. I guess people always bug me about this because I put 71 there, so just go to 7. Those are a few there that you can leave out. Do not do them all. Skip around. Look at ones that interest you. Don't feel like you're obligated to do them all. Use some of the extra ones. Save some of the extra ones for like exam review or something like that. All right, so it's 9:24. Maybe what I should do is, should I pick a question that you should have done by the end of the period? How about, well, yeah, you have to do at least one. How about everyone, if you haven't given the one in the problem package, the one about the lady going through the yellow light, if you haven't done that one yet, do that one before 10 o'clock, and I will correct that one at 10 o'clock. Okay, Chris, because that's the one you want, right? And you want one, right? That one too, so that's is it number 15, is that right? Okay, so give number 15 a try by the end of the period, and then I'll correct that one.
Oh, yeah.